Good morning, good evening, good afternoon. We have a full house. It looks like this webinar is oversubscribed, and it's a pleasure to have with me today the Chief Scientist, Mr. Roberto Bagnara from BUGSENG. Today we'll be talking about MISRA. If you're a programmer, if you know anything about software, you probably know MISRA. Well, it's a powerful concept. Is MISRA a tool, a philosophy, a practice? Well, it's powerful. You'll find out today. The key is using that power without the pitfalls. There's some challenges. Let's see what we have in store for you today. Well, AFuzion does these monthly training webinars, and it's such a pleasure to have Roberto with us this month. A little quick summary of our companies. AFuzion has over 250 successful safety critical and aviation projects that we work on. And we have 45 engineers that practice process optimization and templates, checklists for safety critical projects. We have mentoring, we do training. I think we've trained about 25,000 people around the world. We have over a total of 300 successful safety critical projects worldwide. And all of our clients state that they either have or would hire us again. And Roberto's BUGSENG. Roberto, would you like to tell us a little bit about your company?
Sure. So BUGSENG is a supplier of tools and services for software verification. So the company started inside the University of Parma more than 10 years ago, and it leverages on technologies built on more than 20 years of research. The main product is the Eclair software verification platform, which is qualifiable with respect to the requirements of most functional safety standards, mainly DO 178C and ISO 26262. And in addition to providing this tool, we of course do training, especially MISRA training, and we also do consulting services to help our customers to comply with MISRA and other standards.
And again, it's really a pleasure to have you with us here this morning, evening, and afternoon. Folks, you know how our training sessions work. We like to give you a little quiz to begin. This is simple, 6 questions. Number 1, see how you do, answers at the end in 45 minutes. Software testing is the best method to improve quality. True or false? Safety critical domains, aviation, medical, nuclear, industrial control, automotive. They provide good information and recipes for coding in C and C++. True or false? Humans are effective and efficient in reviewing and optimizing C code. Number 4, with great static code analysis, no other software verification is necessary. Dynamic software testing is similarly efficient. You know, dynamic, executing the program, is similarly efficient and effective as static analysis. And number 6, verification and validation are similar. That's why we call it V&V. Interesting. Answers in 40 minutes. Now, real quick, what is safety critical really? Well, it's a system, and probably you're working on one now, whose failure or malfunction could result in one or the more of the following bad things: death, injury to people, loss, damage to property, equipment, or harming the environment. Well, at the same time, we're concerned about software reliability. That's the probability that failure-free software, software without anomalies, defects, will operate at a specified period of time in a safe environment. For safety critical systems that contain software reliability, you know, is a really important factor that affects that reliability. So this comes down to the pillars of the process, the ecosystem. In safety critical, we have a planning process. It's red, it's at the beginning. It's small, but it's important. Later, we assess the engineering to those plans. Then we have the development process. After we've defined the plans for compliance, configuration management, quality assurance, verification, validation, development. Then we develop. We might use Agile, and yes, we do use safety critical Agile. We could show you how to do that in a separate webinar. And we have the old waterfall. Nobody does that. Maybe V model, model-based development, spiral method. There's many different ways we can develop software. And then you have the integral background processes, verification, validation, CMQA, continuous in the background. And safety critical has 4 pillars for success. Software requirements that include the safety aspects decomposed from the system. That's the foundation. Then a good and safe architecture, the design of that software. And then today's session is the code, how to construct code that meets the requirements, is compatible with the architecture design, and that is ultimately the tip of the pyramid, validated and verified. Okay, now consider, all of you, I hope, participate in code reviews. Some of you perhaps have seen, I know you haven't done this, but you've seen a code review where, yeah, what happens? You just look at the code. Yes, this looks like great code. It weighs 4.3 milligrams. No, no, no. A proper safety critical code review has 6 inputs. We say at AFuzion, if you don't use all 6, no problem, do it again when you will. So can you think what the 6 inputs to a code review are? Next slide. You have to have the code, some kind of checklist, and then today's session, a coding standard. Okay? How should that code be constructed? How is it made and deemed affirmed safe? Then you have the software design. You consider, of course, the software requirements, but then which requirements trace to that code? You complete the review. Any action items, defects are fed back. You fix it, you do it again. Let's look at number 3, that coding standard. MISRA is the world's most popular basis for a coding standard. It was originally defined by the United Kingdom motor industry. That's automotive, okay? But today it's international and covers all industries. It comprised, and the rules keep growing, but today it's 197 rules that are presented in the form of a coding standard, okay? So we use this coding standard to ensure that we have great code. At this time, I'd like to introduce you to Mr. Roberto Bagnara, who I told you about, and he is going to tell you some really cool things about MISRA C. Okay? Roberto, I am going to make you the presenter.
Okay.
And hand it over to you. Roberto, you are now the presenter.
And I am showing my screen, and you should see my slides. And how should I hide the control panel? Okay, this way. Okay, so I will go through a few sections in this part of the presentation. First, I will explain some important things about the C language, in particular the fact that the C language is not fully defined. There are some behaviors, actually several of them, that are not defined in full. Then I will introduce MISRA C, and I will present a very, very small selection of the guidelines to give you an impression on what it looks like, and I will then explain that it is about prevention. It's not bug finding. So they are 2 different things. And then I will give a very short static analysis demo showing MISRA C at work in flagging some famous bugs. Okay, first a disclaimer, I am a member of the MISRA C working group and also of WG14, so the ISO standardization committee for the C programming language. However, the views expressed in this presentation are mine and not necessarily the views of the working groups I mentioned. So let's start with the C language. So C has very strong advantages, and they are of an economical nature. So first thing, C compilers exist for almost any processor, from tiny devices to supercomputers. C compiled code is very efficient and without hidden costs, meaning that a competent expert programmer, modulo the fact of multi-core, can predict more or less the running time of a piece of code he or she understands. C allows writing compact code. There are many operators that are built in, so you can write quite complex things with limited verbosity. It is defined by an ISO standard, and the C language, possibly using common compiler extensions, allows easy access to the hardware, which is essential for embedded programming. C has a long history of usage included in critical systems, and C is widely supported by tools. So these are all advantages. There are also disadvantages. And the main thing is that the C language and the working group that standardizes it has always been faithful to the original spirit, which a little bit joking, we might express with this commandment. So trust the programmer, let the programmer do anything wanted. Speed is more important than portability. And as we all know, this is bad for safety and security of the application. So let's see where the problem comes from. So it comes basically from the notion of behavior in the C standard. Here I am referring to the C99 standard, but all the other versions of the standard are the same for this. So behavior is something that is visible or observable at the, from the external world. So something that happens inside the program is not observable. For example, if I write increment x, unless x is a volatile variable, the fact that really in the machine x is incremented is not guaranteed. It is as if it was incremented. And in fact, the compiler adopts the so-called as-if rule, saying that the compiler is allowed to do any transformation that ensures that the observable behavior is preserved. This is not a peculiarity of C. It is common to many other programming languages. It is common to all programming languages that admit an optimized compilation implementation. Because in the as-if rule, we have most of the opportunities for the compiler to optimize code. Among the behaviors of C, there are classes that are not completely defined. We will see three classes that are dangerous. The most dangerous one is the class of undefined behavior. It's behavior that arises when some non-portable constructs or erroneous program constructs or erroneous data is used. And in this case, the ISO standard imposes no requirements. This means no requirements whatsoever. So a program that has undefined behavior may crash, it may exhibit behavior, erratic behavior of any kind, it may even format your hard disk. So it can just do anything. What it means is that the compiler assumes that undefined behavior does not happen. If it does happen, the programmer has violated the contract, so there is no warranty. Let me explain this with an example. Among the many undefined behaviors, there is this one. The program attempts to modify a string literal. A string literal is a string constant, so something you write within double quotes. Here is an example. We have a string literal which is hello with 3 exclamation marks. And the programmer, in order to remove 2 of the 3 exclamation marks, decides to write to the string literal a null termination at position 6. Well, this doesn't work necessarily, and because it is an undefined behavior, so the program can do anything. There are several reasons why this is undefined behavior. I will just give you one now, and I will give you another one later. The first reason is that string literals might be allocated into read-only memory. And if you try to write to read-only memory, you can get another exception that from the point of view of the program is unpredictable. And this is why it's undefined behavior. Then another class is unspecified behavior. It is when there are two or more possibilities to implement one thing and the standard decides not to give any further requirements. So the implementation can do one thing or the other, and it doesn't even need to document the choice or to be consistent with the choice. Let us see an example. One of the things that is unspecified behavior in C is the order in which the operands of this addition operation are evaluated. So it is equally valid for the compiler to generate code that evaluates hello first and word second, so that the output will be hello word, which is probably what the programmer intended. However, it is equally valid for the compiler to generate code that first calls word and then hello. And in this case, the output will be word, exclamation mark, hello, blank. Okay, so this needs not be documented by the compiler vendor. And it also can change. For example, if you increase the optimization level, this can change. Or if you enable debugging, this can change. Moreover, if I complicate the example, instead of returning immediately, suppose that I do hello plus word 5 times. There is no reason why the compiler couldn't call in the first instance first hello and then word, and in the second instance the other way around. And no requirements which about consistency or doing always the same thing or providing documentation to this effect. The third category is implementation defined behavior. This is unspecified behavior, but the implementation has to document the choice and has to be consistent with the choice. So everybody knows implementation defined behavior because everybody knows that there are C implementations for 16-bit machines and there are implementation for 32-bit machines. So the size of int, for example, is one of the 112 implementation defined aspects of C99. And so why is C not fully defined? We have seen that there is undefined behavior, unspecified behavior, implementation defined behavior, and we skip the fourth category, local specific behavior, because it's not so important for this presentation. So why is this the case? And the reason is, again, economic, because implementing compiler is easier, and because implementing efficient compilers, so compilers that generate fast code, is much easier by this choice. Let us see this in detail. We have seen already that if a program attempts to modify a string literal, then it is undefined behavior. We have seen one reason. Another reason is memory efficiency. In a program, we might have two literals, one tail and the other head tail. Well, the compiled program can store in memory just head tail and use a pointer to the fifth character whenever it needs a representation of tail. So changing one string, if this was allowed, would result in changing also the other string. But the compiler can assume this will never happen because it is undefined behavior. So we have seen a second reason for this. If we try to modify string literal, two possibilities at least. One is that the string literal is in read-only memory and we get another exception. The other, we don't get another exception. We modify one string literal, we believe, but in reality, we might have modified other string literals. Another example is very instructive. So the behavior is undefined whenever an expression is shifted by a negative number, so the shift count is negative, or by an amount greater than or equal the width of the promoted expression. So It's rather easy to understand why negative shift counts are disallowed, because if they were allowed, what might be their semantics? What might mean to shift a quantity -2 position to the right? Well, we might decide that it means shifting 2 position to the left, but if this was the language definition, the compiler would have to emit instruction to check the sign of the shift count, to negate it if it was found negative, and to reverse direction of the shift. This is not in the spirit of the language. The spirit of the language is speed, speed, speed. So this is undefined. So it is a little bit more complex to understand why it is undefined behavior, shifting a 32-bit quantity 32 positions to the left. So one might say, well, I am pushing 32 or more zeros from the right, so the result should be 0. No. And the reason is that on very popular architectures like the Intel ones, the first thing that happens to the shift count is that it is masked. Only the 5 low order bits are retained. And this is done in order to make it easy to predict the maximum execution time of the shift operation. So on these architectures, shifting by 32 position is the same as shifting by 32 masked, which is the same as shifting by 0 positions, which is the same as doing nothing. So also in this case, C leaves this behavior undefined for speed and ease of implementation. And this is a general principle. Whenever it is possible to compile a high-level construct in C into a low-level machine instruction, this is done. And this is the reason why we have so many behaviors that are not completely defined. So let us introduce MISRA C. Here is the history of MISRA C. As Vance said, it started in the automotive field. Ford and Rover were developing their in-house coding standards for C. They joined forces in the setting of the MISRA project, and they produces MISRA C 1998, the first edition of the MISRA C coding guidelines. And now we are at the 3rd edition, and MISRA C, starting from its inception, has influenced basically all the C and C++ coding standards that have been developed afterwards. So before introducing some guidelines of MISRA C, let me point out that the weakness of the C language comes from its strength. So the positive and the negative aspects are really tied one another. They are not easy to separate. So, for example, the fact that it is easy to write efficient compilers for almost any architecture, as I explained, is one of the reasons behind the non-definite behavior. Okay, code is compiled down to machine instruction, and since there is a variability between machine instructions, there is variability in this aspects of the C language. The fact that it is easy to write efficient code with no hidden cost, it's because there is no runtime error checking whatsoever. So, for example, if you want to make sure your index is not exceeding the array bounds, you should have to write the checking code yourself. The language does not put it in your place. The fact that there are many compilers defined by an ISO standard then is another reason behind non-definite behavior. So ISO working groups standardize existing practice. So when there are 2 C compilers that are doing the same thing in different ways, then often non-completely defined behavior is the only way forward. Okay. So the fact that it is easy to access the hardware is also the reason why it is so easy to corrupt the program state, for example, by overwriting the stack. And the fact that you can write compact code, it's caused by the same language features that allow abusing the language. So to write a completely obscure code is possible because of the many built-in operators and the limited verbosity. So several features of C are in sharp conflict with safety and security. So for safety-related application, industry has found this solution, which is called language subsetting. So the point is that you don't write your applications in C, you write them in a safer subset of C. Okay, language subsetting is mandated or recommended by all safety and security related industry standards. So BO 178C to start with, and also all the other basically. And today, the most authoritative language subset for the C programming language is MISRA C, and this is the reason why we are talking about it today. Okay, so let me present the guidelines briefly. So MISRA C 2012, the third edition, first revision with Amendment 1, contains a total of 175 guidelines. I'm not talking about rules because rules is a specific name. So the guidelines are, a guideline is either a rule or a directive. It is called a rule when information concerning compliance is fully contained in the source code and in the implementation defined aspect of the tool chain. So a consequence of implementation defined behavior is that a piece of C code without any information on the implementation of C you are using means nothing. In order to understand what a piece of code does, you need to know the size of integers, you need to know whether plain characters are signed or unsigned. You need to know everything about all the implementation defined aspects. In contrast, a guideline is called a directive if the information about compliance is not fully contained in the source code. You need to know the requirements, the specification, the designs, and in some cases even the compiler intention in order to decide whether you are complying to a directive or not. And the MISRA C guidelines are given a category. They are either mandatory or required or advisory. They are mandatory when you have to comply. So no deviation is possible. So you really have to comply to every mandatory guideline, otherwise the project cannot be called MISRA C compliant. When the category is required, you have the choice. You might comply to the guideline and you are done, or you might deviate from the guideline. And this means that you have to raise a formal deviation. You have to write short, usually a short document, explaining why you are deviating, explaining why it is advantageous to deviate, and why the safety of the project is not endangered by this deviation. I am simplifying, of course, but this is the idea. Advisory guidelines are instead just recommendations. So they should be followed as far as it is reasonably practical. Formal deviation is not required. However, at the end of the project, you have to list all non-compliances or with respect to the advisory guidelines. So let me start presenting a small selection of the guidelines. So rule 1.1, the program shall contain no violations of the standard C syntax and constraints and shall not exceed the implementation translation limits. This is a very important rule. It says the code has to be written in C, not in something else. Okay, so you cannot go beyond the standard C syntax. You cannot violate the constraints of the C syntax, and you should not exceed the implementation translation limit. This rule is required, meaning that you may deviate it in some cases if you provide evidence that it is needed and safe. And this applies to all the version of the C programming language. So let me explain why this rule exists. So first reason is that when developing the MISRA guidelines, things that are outside the C standard syntax and constraints have not even been considered. So no claim about safety can be made if you go beyond the C standard. And another very important reason is that a conforming implementation does not need to generate a diagnostic when a translation limit is exceeded. And an executable can still be generated. So what is a translation limit? Every implementation of C has limits. For example, the significant part of identifiers. So there are some linkers that only consider the first, I don't know, in extreme cases, 6 very old linkers. In other cases, 31 characters of identifiers. So if 2 identifiers differ in the portion that is not significant, this is undefined behavior. Another example is the maximum depth to which you can nest conditional compilation instruction in the preprocessor. So sharp if def, and similar. Okay, so in order for a C90 compiler to be called the C90 compiler, it is enough for the compiler to implement a depth of nesting up to 9. If you exceed 9, well, the compiler might not even give you a warning. And then the code you obtain, the object code you obtain is basically you don't know. And also there are many compilers out there that do not diagnose constraint violations. So they accept code they should not accept. Okay, the code is basically accepted by mistake. And this does not give any guarantee about the code that is produced. Let us move to another guideline, rule 3.2. It's a rule about comments. I have chosen it on purpose because someone thinks, what might be the problem with comments? Well, comments are dangerous. This rule says line splicing shall not be used in / comments. What is line splicing? Is the possibility of joining physical source lines of code into logical source lines of code by using a backslash at the end of the line. And the point is that if you mix line splicing with / comment, you may inadvertently comment out code. Here is an example. We have a / comment, and the / comment contain an indication written by the programmer that ends with a directory, a folder path in Windows notations, so with the backslash. However, since this backslash is the last character in the line, then critical function is as if it was written here. So critical function, which is a function that presumably it was critical to be called, it will not be called because it is in a comment. So later stages of the compiler will not even see the call to critical function, and the compiler will give you no warning about this. So you basically are completely unaware of the fact that you are not calling the critical function. Another rule is rule 13.2. It says that the value of an expression and its persistent side effects shall be the same under all permitted evaluation orders. So I have already talked about unspecified behavior. There are orders of some things that is not defined. So we have seen that, for example, the order in which sub-expressions are evaluated is unspecified. But there is more to this rule. For example, there are situations in which you can also end up with undefined behavior if you violate this rule. For example, if you try to modify an object more than once between 2 sequence points. Okay, so let me show you an example. Here we have a piece of code. We have 2 volatile variables, tcnt1 and tcnt2, and one of the unspecified behavior of C is in which order the arguments of a function call are evaluated. So here we might evaluate first tcnt1 and then tcnt2, or the other way around. The compiler can do either thing. And however, since the variables are volatile, reading one of them triggers may trigger a side effect which is externally visible. And so we don't know which side effect is triggered first. So in order to comply with the rule, we may introduce local variables so as to sequentialize the two read operation in the way we want. And notice that any decent compiler will not let you pay any price for having introduced these two temporary variables. Okay, so let me explain some generality about MISRA-C. The point is that MISRA-C is not a tool, okay? It cannot be separated from the process of documented software development it is part of. And in this case, is a very, and in this aspect, it is a very good match for DO178C, okay? The use of MISRA-C in its proper context, so documented software development, is part of an error prevention strategy. This has very little in common with bug finding. Okay, bug finding is the philosophy whereby you program as you want, without constraints. You compile the code, you have a bug finder, the bug finder will find some bugs. The point here is to prevent entire classes of bugs with MISRA-C. So the point to start with, the violation of a guideline is not necessarily a software error. For example, there is intrinsically nothing wrong about converting an integer constant to a pointer. Okay, and to the contrary, it is also needed. This is something that is needed, for example, when you want to address memory mapped registers. However, since integer to pointer conversions are implementation defined and they also have undefined behaviors, there is a rule in MISRA-C that suggests avoiding them everywhere apart from the very specific instances where you need them and where they are safe. And in fact, it is important to observe that the deviation process is an essential part of MISRA-C. And the point of the guideline is almost never, you should not do that. The point usually is, look, this is dangerous. You may only do that if, one, it is needed, two, it is safe. And if you can explain in 30 seconds to your peers that this is really the case, that this is really needed and this is really safe. If it takes half an hour of work to explain that the thing is needed and safe, it's too complicated. So it's much better to comply to the guideline. And in fact, one useful way to think about MISRA-C and the processes that are around it is to consider them as an effective way of conducting a guided peer review. In an ordinary peer review, you will sit down with your colleagues looking at the code, and here you will have the tool that points your attention to dangerous things. Okay, so with this, in this way, it is possible to rule out most of the C language traps and pitfalls. So this doesn't mean that you will, of course, that your software will be correct, but it means that once you are MISRA compliant, you can reason about the program in a reliable way at the source code level. Okay, so another aspect that makes MISRA-C completely different from bug finding is the importance that MISRA-C assigns to reviews of all kinds: code reviews, reviews of the code against design document. And in fact, many MISRA rules have to do with code readability and understandability. So now I will give you a short presentation about how it looks like to work with a C static analyzer. So I have prepared here, a small presentation using Eclair, which is our static analyzer. Here we could configure the project, tell which are the toolchain components that Eclair will intercept automatically in order to extract the implementation defined behavior, and then at the end we can view the results. So let's go straight to this part where we view the results. So we have several violations of the MISRA-C guideline. We have enabled some selected MISRA-C guidelines, and let me go through them in order to give you an idea about what they are there for. So let's start with Directive 1.1. It's a directive of MISRA C saying that any implementation defined behavior on which the output of the program depends shall be documented and understood. So the point is that there are, in this version of the language, more than, as I said, more than 100 implementation defined behaviors. And so you should, in principle, document and understand all of them. But luckily, this program, this small program I'm analyzing, definitely depends on 12 implementation defined behavior. And the tool is telling me on which I am depending. For example, the program is depending on the number of bits in a byte. This is not always 8. There are implementation of C where the number of bits in a byte is 16, for example. Okay, so this program depends certainly on 12 implementation defined behavior and possibly on other 18. So I have to document or take note of 30 implementation defined behavior. So you see that a tool can still help even in checking directives. Let me go through some other directives. This is Directive 4.6. It says that you shouldn't use the basic integer types provided by the languages, such as int or float, because it is not clear what they are actually. So you should always use identifiers that have an indication in their name of the number of bits and of signedness. For example, this is compliant, int 16t. Okay, it's a 16-bit integer, so this is compliant with the directive, whereas the type float or the type int, they are not compliant. Directive 4.7. If a function returns error information, then that error information shall be tested. Here we have a violation. Scanf might fail. It might fail because the stream from which it is reading has been closed. So, and the tool is saying, look, here you are calling scanf, and you are not testing the return value if it is EOF or not. Okay, so this is a problem because if you have got EOF, then the floating point variable D will not have been properly initialized. But then you use it. You see the call to foo of D. Okay, so this is a potential source of problems. 4.11, the validity of values passed to library function shall be checked. You see that here we are calling the abs library function whose behavior is undefined if y is a minimum signed integer, so the most negative value. And here we are not checking it, so we are just calling abs with a function argument, so we are violating the directive. 4.14, so the validity of values received from external sources should be checked. Again, this here the tool is flagging this call of scanf. So we are reading a floating point value from the outside world. Here we can end up with anything, with not a number, with infinities. So we shouldn't trust anything that comes from the external world. So the value of not just the return value of scanf should be checked. This should be checked certainly, but after we have checked the return value of scanf, we should also check D to make sure. Okay, and here is another potential problem, and here we are not checking the return value of getChar. getChar might return EOF. Okay, and you don't see here a call of getChar. Why? Because it's in a macro. So this gives me a possibility of showing you the difference between a good tool and a bad tool. A good tool will show you the code before pre-processing, in which you don't understand. and after preprocessing. Here is the same piece of code after preprocessing. Now you see the call to get char, and the tool also shows you the definition of the macro that causes get char to come into play. So 4.14, rule 2.1. Okay, here we have an instance, you can see it, it's the famous Apple's SSL go to fail bug. Here we see how this violates in several ways the MISRA coding standard. The first way that we see it is as a violation of rule 2.1, saying that a project shall not contain unreachable code. Okay, so why is this unreachable? It's unreachable because of the go to fail that is here. Okay, this go to fail, which is spurious, it's a repeated line from the one above, makes is such that this if then else will never be reached. We have another violation here, and this function is not reachable. Now we don't understand why it's not reachable, but we will see in a minute with another violation that the point is that this test is always sorry. It's unreachable. It's unreachable for the same reason as above. Because it's unreachable because of the repeated go to fail. 2.2 says there shall be no dead code. Here we have an instance of the Ariane bug, and you see one of the ways in which here we see the reason of this violation. So this initialization is dead code. And why it is dead code? Because the value of x is overwritten. And why is it overwritten? Because here we did a mistake. Here we wanted to write an equality test, but by incidentally omitting the second equal sign, we have an assignment. So the value of x is always overwritten by this int 16 min. So this is one of the violations we get if we do this kind of mistake. So 8.3, here this is interesting because this is an undefined behavior. So in one translation unit, p.c, it is said that function qx takes an int 16t, but in another translation unit where the function qux is defined, the argument is int 32t. You see? So the linker would simply not be able to flag this mistake because type information is usually does not usually arrive at the linker stage. So here we have an undefined behavior. However, there is a rule saying that all declaration of an object or function shall use the same names and type qualifiers. So here we are using different types. So this is one kind of mistake that we can prevent with MISRA. With this rule of MISRA, we can also prevent another kind of mistakes. The names of the parameters should be the same. You see that here in these sample programs, we have in one instance of the argument of the bus function is that they are both of type float, so the type is okay. However, here in the external declaration, the argument is said to be a delay in milliseconds, whereas here the delay is in seconds. So that's another violation of the rule. Types are okay, but the names are not okay, and this may be a big problem indeed. 10.3. The value of an expression shall not be assigned to an object with a narrower essential type or a different essential type category. So let me skip the technicality. The point is this, that here we are implicitly converting a floating point value to an integer. And this is an instance of the bug that makes the Ariane 5 explode. So in the conversion from a floating point to the integer, and overflow caused problems that compounded to the destruction of the Ariane 5. Okay, so this is flagged. It is flagged by this rule 10.3. There are other violations of the same rule here. So let me continue. 10.4. Both operands of an operator in which the usual arithmetic conversion are performed shall have the same essential type category. So here we have a violation. This is interesting. Here we have the tool is saying, look, here you are comparing a signed integer with an unsigned integer, because this is the code after preprocessing. 0 expands to 0u, so 0 is unsigned. Well, what happens here is that the rules for implicit conversions in C mandate that it will be the signed value to be converted to the unsigned type. So what will happen is that when x is negative, and this is the case here, when x is negative, it will be converted to the unsigned to an unsigned integer. So it will result always in a very large positive value. So this comparison will always be false. Okay, and this I mean, for the unsuspecting C programmer, this is striking because it's just a comparison, and the point is that you should never compare signed with unsigned. And similar problems arise if you do operation between mixed signedness integers. 10.4. So 12.1, the precedence of operators should be made explicit. In this program, so it's a rule that you have to put enough parentheses to make clear what you mean. So now looking at this, you don't understand what is the problem, but you understand it here. Looking at the preprocessed code, you see that here we have a problem. Okay, not simply we miss parentheses, but what happens is not what we wanted. So here the intention for the programmer was to, given a delay in seconds, to add 1 second and then convert the result to milliseconds. Okay, but it is not what happens, because after preprocessing, because of how the macro is written, it is not the result of the addition that is multiplied by 1,000. It's just the 1.0 which is multiplied by 1,000. So this is one of the mistakes that this rule is meant to prevent. Let us look at 13.4. We have already seen this. It violates another MISRA guideline here. The mistake was to have incidentally omitted an equal sign. So what was thought to be a comparison has become an assignment operation, and this is flagged by this rule. Okay. So 14.1, don't use loop counters of float type or floating point type, because then it is very difficult to predict the number of iterations, because floats are complex, they are subject to rounding. So in fact, in this example, it is quite possible for this loop to loop forever. 14.4, the controlling expression of an if statement should be Boolean. And yet another rule that allows us to flag this problem, which is a common weakness enumeration number 481, saying that we write an assignment when a test was meant. 15.6. The rule 15.6 says to always write braces in the if then else in the bodies of the if then else. So here we have a violation, and if this was done properly, we would have avoided the Apple SSL bug. The value returned by a function having non-void return type shall be used. Here we are ignoring, we have written ourselves a function that is returning an integer, and we are not using its value. 20.7, expressions resulting in the expansion of macro parameters shall be enclosed in parentheses. So here we are pointed at the bug. The problem of this macro definition is that X should have been written in parentheses here in the expansion, and then we would have been sure that the multiplication by 1000 would have really for the value of X and not from some sub-expression comprising X. 22.7, the macro if shall only be compared with the unmodified return value from any standard library function capable of returning if. Here is another bug in this program. The problem is that on this implementation, plain char is unsigned. So due to this cast here, the comparison to make sure we are not getting F is not functioning. So this doesn't work anymore because what happens here on this implementation, EOF would be -1. Okay, by converting it to char, we would get 255. So C would contain 255, and when we do the comparison, it's too late. So the comparison would be, is 255 different from EOF? And it would be, okay, so this is a bug. Okay, so this was the very short demo, and to conclude this part of the webinar, let me conclude. So this part. So C is the most used language for the programming of embedded systems, and the advantages of C come with corresponding disadvantages, and this is the reason why we want language subsetting. MISRA C is the most authoritative subset of C for the development of critical systems. MISRA C is not bug finding, it's part of a software development process, okay? And the key for smooth and successful adoption of MISRA C into an organization are good tools that are qualifiable, and proper training. Okay, now I give back the control to
Very good, Roberto. That was fantastic. I've got the screen control. You should see my slide 12 online. Yes. Everyone, we really appreciate Roberto. He's the chief scientist from BUGSENG, and you've got a great introductory MISRA lesson there. So fantastic. We do have a few questions, just a couple moments for questions. Roberto, one person asks, is there any particular tool you recommend that checks for compliance to all of the MISRA rules? Do you have a response for that one?
Well, of course, I have a conflict of interest because my company produces such a tool. So yes, my recommendation is to use Eclair.
Okay. Yeah, of course, there are other tools, and Roberto's company has a very good tool in Eclair as well. Another question, if we use MISRA, do we still need the code review? I'll go ahead and take that and then have Roberto expand on that. You know, the code review without static analysis, MISRA checking, is helpful to look at the code, but humans, remember, are not good at looking at code, okay? And we're going to look at our quiz answers in just a moment. It'll explain it a little more there. The best code review, we think, is when you use a tool such as Eclair or another tool to enforce the MISRA constraints, but then use the human. Remember the inputs to the code review we displayed an hour ago, those 6 inputs? Well, the requirements are the most important. So does the code meet the requirements? The tool's not good for that, of course. So you still need a code review, but it can be much more efficient and much more attuned to what the humans do, which is assess code for requirements. Roberto, any elucidation or clarification you'd like to make on that?
No, I think you are correct. You of course need the code review. The point is that if your code is MISRA compliant, it's much more readable. So the code review will be much easier, and you will have already rooted out many of the C traps and pitfalls.
Good point. Good point. Let's look at the quiz answers. See how you all did. Look at this. They're all false. Software testing is the best method to improve quality? No, no. Prevent the bugs, have good requirements, good coding rules, do the static analysis. Number 2, safety critical domains provide good information and recipes for C coding? Definitely not. All the more reason we need static analysis, right? MISRA. Number 3, humans are effective and efficient in reviewing and optimizing C code. Oh, humans, we can be a little arrogant, a little conceited, right? We think we are, but we're truly not. Remember, computer executes billions of instructions per second. Humans, when it comes to this, don't keep up. Use a tool. Number 4, with great static code analysis, no other software verification is necessary. There's 2 forms. There's prevention of errors and there's detection of errors. If our prevention is perfect, then we don't need the other testing. But our prevention can never be assumed to be perfect. So we actually need both. Number 5, dynamic software testing is similarly efficient and effective? No. In fact, Barry Beam, Kokomo, the father of software engineering economics, says that prevention is 700%, 7 times more efficient than detection. So static analysis helps us prevent errors. It's more efficient. And verification and validation are similar? Definitely not. Verification, does implementation meet the requirements? Validation, do I have the right requirements? Validation is more important, but then verification is the yin yang. So there you go. Roberto, any final words from yourself before we show our last slide here for more information?
No, it's okay. Your explanation was perfect.
Oh, fantastic. Well, folks, if you'd like more information from either AFuzion or BUGSENG, check out the links here. We won't be sending out the copyrighted materials, but we will be sending you a link to the video. It takes a few days to process that, and everybody who registered will get a link. And please tell your colleagues we're sorry that some of them could not get in. Our monthly webinars are getting more and more popular. Sorry about that. So there are videos on BUGSENG's YouTube channel, AFuzion's YouTube channel, and we both have material, technical material you can download for free for additional information, or simply send us an email. So we are 4 minutes over schedule. What do you call a safety critical project 4 minutes behind schedule? We call it a big success. Roberto, thanks so much for joining us this month.
Thanks to you. Bye-bye, everybody.
Thanks, everybody. Bye-bye now.